Okay, let's talk joint moments. Now, what's interesting is the term moment and torque are used interchangeably. They mean the same thing. Mathematically, moment is probably the better term to use, and it's pretty common to use that. But torque and moment will mean exactly the same thing. In fact, it's actually the same equation for each of those. So why do we have two terms? Well, it depends on which circle of friends you have. Some people will use moment, some will use torque. In biomechanics, probably 20 years ago, it was most common to use torque when discussing the tendency of a force to cause rotation. But probably more contemporary, it's moment is the better term. Seeing that I did some of my studying over 20 years ago, I still use the term torque. It just is a habit, but torque and moment will be used interchangeably. So on your terminology worksheet, just realize moment is the tendency of a force to cause rotation, and is the exact same definition and equation for torque. And I just want you to be ready to hear either moment or torque and understand that they represent the same thing, the same equation is used, and the same units are used to represent each of these terms. So I try to be consistent and use joint torque, but you'll see it in the literature that joint moment is very common to use as well, and both of these mean the tendency of a muscle to cause rotation. That is, the muscle generates a force. That force is acting some distance from the axis of rotation. That is a joint moment or a joint torque. Same exact concept for both of these terms. Sometimes I'm lazy and I'll mix these terms up, but they mean the same thing, so it's all good. All right, so let's look at an example, because this is what we want to start using our torque information to understand, is how human movement happens and how to analyze human movement. So let's look at something very simple like elbow flexion. So I've just drawn an upper arm with the forearm here, and I have the muscle force. In this case, I have the bicep brachii acting some distance from the axis of rotation. I also have another force. In this case, let's just consider the situation where I'm holding, or this person's holding, a weight, and there's the force of gravity acting on that weight. Now, the forearm also has some mass and therefore has some weight, and I could draw a third force here to represent that. I'm not going to. I'm going to try to keep this situation real simple to begin with, and you'll see as we progress, we'll start adding additional forces to try to understand things to a finer detail than what we're doing here. Likewise, I could also add in the tricep brachii as an antagonist muscle if we're doing elbow flexion. Again, I'm not going to right now. We'll talk about that later. And there's other muscles that cross the elbow joint to cause elbow flexion, and I'm going to ignore those at this point and just deal with the force of the muscle from the bicep brachii. We'll start with something simple, and then we'll make it more complicated as we go along. So we want to do an angular kinetic analysis, and if you remember from a previous video, I introduced the steps for an angular kinetic analysis, and this is how we're going to do it. So anytime we are looking at joint moments and joint torques and trying to understand what's happening, we'll do this process. The first step is we want to identify the torques acting about the axis of rotation. In this case, we're dealing with elbow flexion, so we're dealing with the elbow joint, and we're looking at torques that would tend to rotate the forearm around the upper arm, or around the elbow. All right. So in order to identify a torque, we need to identify the forces acting on the forearm that would tend to rotate the forearm around the elbow. We'll use this equation to identify and calculate the torque due to each of these forces. We'll assign the direction of the torque, and then we're going to use the equation sum of torques equals I alpha, and we'll link the kinetics, angular kinetics, with the angular kinematics. So we'll understand, if we add up all the torques acting about the elbow joint, we'll understand the product of moment of inertia and angular acceleration. And angular acceleration represents the angular kinematic parameter. So we're just going to go through this process, identify the torques. We do that by identifying the forces. We'll use this equation to calculate each torque. We'll assign the direction associated with each torque, and then we'll put each of those torques into this equation. All right, so let's go back to our elbow problem. I'm actually adding in some other information here. So we have elbow flexion, and so looking at our problem or our drawing, we have two forces, the force of the muscle and the force of the weight acting at the hand. All right, I've simplified the drawing. I've taken away the muscle, I've taken away the drawing of the weight. So let's look at this. We have two torques, torque due to the muscle, and we calculate that torque by identifying or understanding how much force that muscle generates and identifying the moment arm of that muscle. And we'll go through that in a second. And we have the torque due to the weight, which is equal to the product of the weight itself, the force of gravity acting on that weight, times its moment arm. So we've got two things we need to do. We need to identify the moment arm, and then we need to assign the torque direction. I didn't include this as a previous step because this is just part of the equation. But I'll do it now. So identify the moment arm for the muscle force. We draw out the line of application, straight line projection in both directions. And then we draw the shortest distance between the axis of rotation and the line of application of the force. That distance line that we draw has to be perpendicular to the line of application of the force. So this little distance right here, I'm going to draw an arrow, is the moment arm for the muscle. Okay, let's do the same thing for the force of the weight. We draw out the line of application of the force, straight line projection in both directions, and the shortest distance between the axis of rotation and anywhere on that line. Remember, we can also put a line perpendicular to the line of application of force, so 90 degrees, and then move that line down to a point where it intersects the axis of rotation. And that length will be the moment arm for that force vector, all right, the perpendicular weight. Now that we have both those moment arms identified, we can identify the direction of the torque. And remember, we're going to always use counterclockwise as positive reference frame. To do the direction of the torque, remember we did this in another video, we start at the tip of the force vector, we go around the axis of rotation, and we end up at the tail, and we cannot cross the lever arm here. So we're going to start here, we're going to go around the axis, end up here. That rotation, we don't know which way rotation is happening yet, but right now that tendency to cause rotation in the counterclockwise direction, that's a positive torque. So I'm going to go up here, and I'm going to put positive here. All right. Now let's do the same thing for the torque due to the weight. We start at the tip of the force vector, we end up at the tail. We have to go around the axis of rotation, and we cannot cross the lever arm. So I'm going to go like this. Now I'm going to go off the paper all the way up here, come back around here, down here, just so we can see that rotation is going to be clockwise for this force. So that clockwise is a negative torque. So I'm going to put a minus sign. Oops, I'm going to put a minus sign right up here. All right, so now we've identified the moment arm, we've assigned the torque direction. Now we can continue with our angular kinetic analysis. And the next step is to put those torques into this equation, T equals I alpha. So sum of torques acting about the axis of rotation equals the product of moment of inertia and angular acceleration. Now let's follow this through. We have torque due to the muscle. That's a positive torque, which we identified on the previous page of notes, plus negative torque due to the weight. Again, that direction assigned based upon our schematic, that equals the product of moment of inertia and angular acceleration, resistance to change angular motion, and angular acceleration, rate of change of angular velocity. All right, let's look at this a little differently. This will give us a little bit more detail in terms of the kinetics, and even more specifically, the angular kinetics of what's going on. All I'm going to do is I'm going to replace torque of the muscle with FD perpendicular. And I'm replacing torque due to the weight with FD perpendicular. But I'm just assigning the subscript for the force due to the muscle times its moment arm minus, which is coming from that minus sign, torque due to the weight times the moment arm due to the weight. Right? So we can use either of these equations, and sometimes we want to just work with this one if we know the torques, or sometimes we want to work with this one if we're trying to find out some more detailed information about, for example, how much force the muscle is generating. If you think ahead to test questions, as I've done in the past, we look at this equation. If we wanted to identify the muscle force, I need to know everything else in this equation. So remember, you can only have one unknown. So if you want to look at this from a test perspective, I have 1 question, 2, 3, 4, 5, 6 different questions I could ask given this equation, given 2 torques acting about the axis of rotation. So you want to be comfortable being able to rearrange the parameters in this equation so that each parameter is by itself on the left-hand side of the equality sign. In the next video, I'll actually go through an example of putting some numbers in and then following that through to do some calculations. But in this video, I just want to talk about more broadly what's happening between the relationship between of angular kinetics and angular kinematics. So let's just look conceptually what happens if the torque due to the muscle is greater than the torque due to the weight. If we go back up to this equation, if the torque due to the muscle is greater than the torque due to the weight, what direction will the acceleration vector have? Moment of inertia is always going to be positive. So if this is greater than that, if this is 100 newton meters and this is 50 newton meters, 100 newton meters minus 50, that's a positive number. So angular acceleration will be positive. Now remember, be careful. Going back to our angular kinematics section, the direction of rotation is not necessarily positive. The direction of angular acceleration is positive. And that just tells us something about angular velocity, how quickly angular velocity is changing. And we'll go through this more as we start putting some numbers to this problem. All right, well, what happens to the direction of this angular acceleration vector if the torque due to the muscle is less than the torque due to the weight? Well, if you just look at the equation, if this is 50 newton meters and this is 100 newton meters, 50 minus 100 is going to be a negative product on this side of the equality sign. So therefore, I is always positive. Therefore, angular acceleration has to be negative. Now, again, it doesn't tell us which way rotation is happening. All it tells us is the rate of change of angular velocity is going to be negative, which tells us, going back to angular kinematic graphing, it tells us that the slope of the angular velocity versus time plot is going to be negative. All right, we've got one more here. The torque due to the muscle, if it's the same as the torque due to the weight, what happens to angular acceleration? All right, let's go back up, look at our equation. If this is 100 newton meters and this is 100 newton meters, 100 minus 100, it's going to be 0. Moment of inertia is always going to have some number, therefore angular acceleration has to be 0. All right, so from this video, I want to make sure that you understand, one, how to apply this equation or how to get to this final equation, and then 2, how to understand the concept of what happens to angular acceleration given the relationship of these different torques. Okay, thanks everybody.